Hello everyone and welcome to PrepFusion. I am Anish and this will be the lecture 4 for the subject of control system. This is the first chapter that is the basics of control system. So in this lecture, right, we'll study the negative and positive feedback and what is open loop transfer function and what is closed loop transfer function. Here I have forgotten to written, and like how is sensitivity measured and what is the meaning of sensitivity, and few questions on sensitivity. Okay, so in the previous lecture I stopped before the closed loop transfer function, right? So here I will again restart that what is a negative feedback system. So what happens in a negative feedback system is that when the output tries to increase itself, right, when the output is increasing, right, what this system will try to do is decrease the output, right, decrease the output. And if the output is trying to reduce, right, if it is trying to reduce, then what the system will try to do is increase the output. It will do the opposite effect. Let's say this fan, right, so this fan I want it to rotate at a certain speed, or let's say I want certain amount of wind through it, right? Now what happens is, like, due to dust and other things, the fan is rotating slowly. So what this system will try to do is give it more power so that this fan can rotate more fast, so that I can get the desired wind that I need, right? That is what this negative feedback does. It tries to keep the output at the same level, right? It tries to keep the output at the same level, at our desired level, what you want. Like if it tries to, if the system, if the fan tries to destabilize, right, if the wind speed decreases or increases, it will do the opposite effect. If the wind speed decreases, the system will try to increase the power so that the wind speed again goes to that our level. And if the wind speed increases, then the output, the system, what it will try to do is decrease the power so that the again the wind speed gets to our level that we want, right, desired level. So like this is what a negative feedback does. So you can write it for yourself. I can write here, or I will not write. Okay, this is just a rough note. Just what I will write it as, tries to, okay, keep the output at same level. Okay, tries to keep the output at the same level. Okay, so this is important. And at maximum cases, right, maximum cases, it stabilizes the system, the whole system, right? It stabilizes, it doesn't destabilize. Like what do you mean by stabilize and destabilize? All this we will learn slowly. Okay, just write this down, that at maximum stabilize the system. Okay, now what we will do is, like, I forgot to write one thing here, is that some g of s coming over here, and this is the h of s, right, the feedback path, right, gain of the feedback path. And what do you call this difference, right? There is some difference, right? R of s is coming here and this is a subtractor. Okay, this block we'll understand in the program, but you are understanding, right? Some signal plus is coming here and this is negative, right? So what will happen, we'll subtract h of s with this. So what is the value at this point, right? It is just we're taking c of s from here. Okay, just this is very simple to understand. So this is c of s only. So this is the gain block, right? So this c of s will be multiplied with this h of s, right? So c of s times h of s, and what we are doing is we're subtracting this point, right? We're subtracting at this point. So this is known as the difference, d of s, difference signal, right, d of s. Okay, so now what I want, like, we will do is basically calculate the transfer function c by r. Okay, c by r. So what I will write expressions, right? So we write right here. So now this d of s, right, the point here is d of s. Now it will get multiplied with this gain block and we'll get our output c of s. So we can write this is like d of s times c of s, right, c of s. So what I can write here is, d of s times this g of s, right? So now what we can do is like again let me write the d of s, right? What is d of s? D of s is basically the difference of these two, right? Difference of these two. So equals to into h of s. Okay, r of s into c of s h of s. Okay, so this is basically the d of s. Now like what I will do, put this value of d of s, right, in this equation, and we'll find the value of c of s in terms of r of s, right? So c of s by g of s. Okay, what I will do, I will just skip writing s right now. I hope you are understanding, because it will be very heavy task. I will just write simple c by g. Okay, c by g equals to this d, right? And d, what is d? D is r minus c into h. Okay, so again like this is just normal arithmetic. 1 plus h equals to this one, I think. Okay, this one was 1 by g, this is r. So what is c of s by r of s? It is g of s upon 1 plus g of s into h of s. Okay, so this is the value of our transfer function for a closed loop system which has a feedback path gain of h of s, right, and a forward gain of g of s. Okay, so this thing like this will come up many times, so this thing will automatically get you will automatically remember in your head this thing. Okay, this thing will automatically get into your head. Okay, so this is very important. Okay, and this term, right, this term is known as the OLTF of the transfer function, or OLTF of the closed loop system. Okay, I will explain you what do you mean by OLTF of the closed loop system. But first let us study the positive feedback system. Like everything is same here, just one thing is that instead of taking this output, right, taking the feedback, what we are doing, instead of subtracting, we are adding the feedback this output, right? We're adding it. So what will happen this time, if the output tries to increase, right, then this system will help it to increase. Yeah, it will again increase more and more. It will keep on increasing. And if the output tries to decrease, right, the system will try to help it decrease. So the output will keep on decrease more and more. Okay, so in this case, like the output doesn't stabilize. Okay, the output doesn't stabilize. So if the output decreases slightly, it will decrease, the system will help it decrease, and if the output increases slightly, the system will help it increase. Okay, this is basically what a positive system does. Okay, so yeah, let me write it down. If output then it will system will help it increase further. Okay, and if, like again let me copy this actually. Let me like decrease the size of this one also. If it tries to decrease, right, instead of increasing, let me write this here, decreases, then the system helps it in decrease further. Okay, else this will be actually s actually here. decrease further. Okay, so if the output decreases slightly, then the system helps it to decrease further, and increase it will help it to increase further. Okay, so in most cases, right, in most cases it destabilizes the whole system. It destabilizes the whole system. Okay, that is, it doesn't remain into certain value. It goes into some, like, it oscillates around certain value. Okay, most cases destabilizes the system. Okay, so again let us do this. This is again signal D of S. This will this time I will do it a bit fast. So like D of S equals to simply sorry, not D of S, C of S equals to G of S times D of S, right? So now what is D of S? D of S is basically addition of those two signals, right? It was previously subtraction, now it is addition of those two signals, H of S into C of S. Now simply again I will do the same thing. C upon G equals to R plus H times C. This time only difference will be, here we have minus GH by G equals to R. So instead of plus, right, we'll get minus sign. G of S by 1 plus this is not plus 1 minus G. Okay, write S also, right, H of S, and this is the so this is basically the transformation, right? So C of S upon R of S. So for a positive feedback system, this is transformation. This thing will automatically get stuck in your head, because this will be used multiple times. Okay, so like what are the examples of this positive feedback system, right? So one example can be these are yet not like if you have studied analog, you will know. If you haven't, then you will not understand. Like a oscillator, like a Smith trigger, right? Oscillator, what happens? It oscillates, it produces a sinusoidal signal, right, of a certain frequency. Okay, it oscillates around certain frequency. It is never stable. Okay, it always oscillates certain values, right? And Smith trigger also, it is also never stable. It either goes to plus or minus, a comparator circuit basically, either goes to plus VZ or minus VZ. So don't worry if you don't know, that's fine, that's totally fine. This will be studied, like this is a practical knowledge, this will be studied in analog circuits. Okay, so let's say, like, why do I say positive feedback can be dangerous sometimes? Not always, but it can be dangerous. Okay, let's say the washing machine, right? If the fan speed is increasing, and if there is positive feedback, the fan speed will keep on increasing, and what will happen? The fan will get damaged, or the washing machine will get damaged. Okay, so it is also very dangerous in certain cases. Okay, so yeah, that's why they may say that positive feedback is sometimes dangerous. Okay, so let me write here examples. Oscillators, Smith trigger, oscillator, Smith trigger. Okay, so now let me write a few key points, right? Few key points. So first key point is what is negative feedback system? In negative feedback systems are mainly used for designing of amplifiers, because we need stable gain. Okay, and negative feedback system increases the stability, as mentioned earlier. Also, negative feedback system is also known as degenerative feedback system. Why degenerative? Because it is reducing, right? It is reducing the output. Output is increasing, reducing. Okay, that's why it's degenerative. It is not generating anything, it is trying to reduce it, degenerate. And positive feedback system are used for designing oscillators and multivibrators. Like, if you don't know these terms, this is just for knowledge purpose, don't worry. Okay, don't worry. And positive feedback systems decrease the overall stability of the system in most cases. In most cases, the overall stability, right, it reduces. In case of sensitivity also, we'll understand, like, after studying the topic sensitivity. And in positive feedback system is also referred to as regenerative feedback system. Why regenerative? Because yeah, you will understand, right? If the output is increasing, it is helping it increase further, it is helping it increase further, so it is regenerating it, it is giving it some more energy, okay, to increase. Okay, from there you can understand. If so what I was saying is, if no information about the feedback is given, right, by default we will consider it negative feedback. Like they say that there is this feedback of the system, and just like that in the question, no, nothing is mentioned positive or negative, we will consider negative, because that is just generally 99% of the cases there is negative feedback, so we will consider negative. Okay, so in gate also you will consider negative feedback. It's if nothing is mentioned. If mentioned, then though, you know, okay, if nothing is mentioned, then take negative feedback. And if there is no information of the feedback element also, that h of s, right, that h of s, then what do? You will take h of s equals to 1. You will take unity feedback system always. Generally we use the unity feedback system only. Okay, so in general, but we may use it with a gain. So if there is no information given about the feedback element, then by default you will consider unity feedback system. Okay, like mostly you use unity feedback systems only. Okay, so this was one point. Now like let's know what is the OLTF, open loop transfer function, right? So like this is just a terminology. Okay, there is nothing like this is a very big thing and concept, nothing like that. This is just a terminology to like understand few things. Okay, so first thing to note is that just a terminology. This is just a terminology. Okay, so what we'll do is to find the open loop transfer function, right? Open loop transfer function is only valid for a closed loop system. Okay, it is not valid for open loop system. Open loop, the name has open loop, but what does this mean? Basically we'll break the loop, we open the loop, right, and then find the transfer function. Okay, so what we do is break the loop here. We break the feedback, that is break the loop or feedback here. Okay, now then find the new transfer function. Okay, let me copy this. Oh sorry, this is related. So what I will do, I break the loop here. Okay, I break the loop here, and this is a new output. This is c dash of s. What I will do, I will find c dash of s upon r of s. This will be our OLTF, right? This will be our open loop transfer function. Okay, so like how to find this, so basically what is coming here, this is broken, right? Nothing is coming over here, so this is 0 only. So r minus 0 times, like this is going multiplied, right? So this is times the gain block g of s, then this is coming here, right? This is coming here into h of s. Okay, so g of s into h of s equals to this c dash of s. Okay, so now we can find the ratio of r and this. I should write this as r of s actually. So yeah, this is the OLTF, right? C dash of s upon h of s. So OLTF is the product of that open loop gain, like that g of s and the feedback gain, right? So this is the open loop transfer function. Okay, this is the OLTF. Okay, so now I can relate it with the closed loop transfer function that I just derived a few seconds earlier, right? Few slides earlier. So what is the closed loop transfer function? CLTF is basically g of s for a negative feedback system, right? 1 plus g of s times h of s. So how can I write it? Basically I can write this like g into h is OLTF, right? So g of s into 1 plus OLTF. G of s equals to 1 plus OLTF. So this is CLTF. Okay, so now this is equals to, I will write OLTF in terms of CLTF also. Okay, but in terms of numerator and denominator also, what you can do is, but this is not that important, but what important relation we get is, like, I will tell you later, but first let me like talk about this denominator, right? This denominator, okay. So this denominator, right, equals to 1 plus OLTF. Now, like, I haven't taught you what poles and zeros are, but the denominator of the closed loop transfer function is known as the characteristics equation of the transfer function, right? Characteristics equation. So this is known as the okay, let me write it like this only. Characteristics of transfer function. Okay. Characteristics equation of the transfer function. Okay, so this 1 plus OLTF, right, is known as the characteristics equation. Now the roots of this denominator are known as the poles of the transfer function. Roots of the denominator, roots of the d of s, right, equals to poles of the transfer function. Okay, poles of the transfer function, or like not, if you don't understand like this is d of s. So this is equals to roots of characteristics equation. Okay, so like these things you need to understand. So like poles define many things in a system. We will get to know, okay, but for now just try to understand what I am trying to get to. So this OLTF, right, this OL, like this, first let me define what does pole do. Like we'll understand, study this in broader manner in the next few like lectures, but first the stability of the CLT, right, the stability of the closed loop transfer function or stability of the system. Let me write stability of system slash CLTF equals to simply function of poles. Okay, it is a function of poles because it depends on the characteristics equation. Okay, so this thing you just know right now, you just understand right now. I will explain all this in the next lectures. Okay, so now what does the poles depend on? Poles depends on the roots, right? Poles are basically the roots of the d of s. So it is function of roots of d of s. Okay, and like now what are the roots of the d of s? Basically roots of the d of s also depends on the OLTF. Okay, what I am trying to get at is the stability of the CLTF, right? Stability of the closed loop transfer function depends on the open loop transfer function. This will be very important in like next few chapters, all those things. This is just a few important thing. Okay, so stability of the closed loop transfer function depends on the OLTF. Okay, if I change the OLTF, then the stability will change for CLTF. Just this thing keep in mind. If you don't understand this, everything will be cleared in the next few lectures. Okay, don't worry. So if I change the CLTF, right, if OLTF is changed, then roots of d of s will change, and the poles of transfer function will also change. Like due to this, like the roots of the denominator changes, then the poles of transfer function changes, right? And like if poles change, then the stability of the transfer function change and the performance of the transfer function will change also. Okay, I don't have enough space. Let me write it down a bit smaller actually, and write it down in different colors actually. Yeah, if this change, then poles will change. Okay, Okay, so what will happen if pole change, then the stability of the transfer function will change. So oh, and if stability changes, then performance of the transfer function will change. Okay, so I don't really write this, just understand the performance of transfer function will change. Okay, so also one more thing we need to keep in mind for a unity feedback system, right? For a unity feedback system, the value of h of s is 1. So then the transfer function, closed loop transfer function and the open loop transfer function can be related in a better manner. So the h of s equals to 1. Okay, the value h of s equals to 1. So the OLTF, instead of g into h, it becomes only g of s, right? So what does the transfer function in case of unity gain, right? It is 1 plus g of s. Okay, so now I can relate the CLTF and OLTF much in a better manner. Okay, so this thing you need to remember, but also remember the condition is for a unity feedback system, this is valid only. So okay, CLTF equals to OLTF by 1 plus OLTF, but the condition is what? Condition is very important condition, h of s equals to 1. Okay, very important, don't forget this, don't forget this. Okay, so yeah, so basically this is the OLTF, and like now we'll do few questions on open loop transfer function and basic normal things, because we haven't done many questions, right? So first question is, we have to find the DC gain of the open loop transfer function for the following closed loop transfer function. So we have to find the DC gain, right? So we have been given this transfer function, this is the closed loop transfer function, not the open loop transfer function. Okay, now what do I notice here? I notice here nothing is said about the feedback. Okay, and nothing is said about the like the gain of the feedback factor, right? So what I will consider, so if nothing is said, right, like DC gain I will come to, but here nothing is said about the feedback, so I will consider negative feedback. Okay, negative feedback with unity gain, right? Unity gain, negative feedback. Okay, now let's come to like the actual question, that is like what is DC gain? What does DC gain mean? Now there are many definitions. So first definition is DC gain means the gain at zero frequency. Okay, but this is only valid, DC gain is the value of the that transfer function, right, at zero frequency, but this is only valid for a type 0 system. Now what is type 0, what is type 1, I will explain. Okay, but another good example, like a good definition is DC gain is the constant gain of this transfer function, right? Like let's, like this is asked us to find the DC gain of OLTF. Let's say for CLTF, right? For CLTF, what is the DC gain? DC gain will be at t equals to infinity, for the in the time domain expression at t equals to infinity, the steady state gain. DC gain means the steady state gain. At t equals to infinity, what is the value of the transfer function? That is basically what DC gain means. Okay, the at steady state gain. So DC gain, better definition is Okay, let me take another pen. DC gain is a steady state gain. Okay, so now like this is the broader example, but DC gain also means the zero frequency gain, but for a type 0 system. So we'll write here another color. Okay, I need to write this a bit smaller actually. Zero for a type 0 system. Okay, so yeah, this is the definition of DC gain. I will explain you. So like firstly what we have to do is we have to find the open loop transfer function. Okay, this didn't ask us for to find the DC gain of the CLTF. We can anyways find the DC gain of CLTF. Okay, so DC gain of CLTF, what will it be? Simply the value of the transfer function at s equals to 0, right? At s equals to 0. So what is the value of this transfer function? S equals to 0, put s 0, 0, this becomes 0. So we're left with 550 by 400. So it is 1 over 8. 1 over 8, okay. Now, like what we'll do is, this is the closed loop transfer function. We need to find the DC gain of open loop transfer function. For that, we need to find the OLTF, okay. So what do you know? OLTF by 1 plus OLTF, this is unity feedback, right? Is G of S by 1 plus G of S simply. This is the closed loop transfer function. What is given? The closed loop transfer function as 50 by S square plus 20s plus 400, okay, plus 400. So this is the closed loop transfer function. So like now what we can write? What we can write here is that to find the OLTF, right? What I can do? I can do componendo and dividendo, right? Do componendo and dividendo. How I can do? Simply like subtract, like I hope you know. Still I am writing the process here. Plus OLTF minus OLTF equals to, this is in terms of numerator and denominator, so this will be n of s. This is componendo and dividendo, right? Minus n of s, okay. So this thing what I will do, okay. So this just keep in mind, this thing is very helpful for finding the OLTF quickly, or else you can simply do cross multiplication on both sides, okay. But this is much more efficient and faster manner to solve for the OLTF, right? So OLTF will be equals to this numerator, right? 50 divided by this s squared 20s minus 50, right? So 50 s square plus 350, okay. This is our OLTF. Yeah, this is our OLTF, okay. Now in this equation I will put s equals to 0. So this is also G of S right now, of OLTF equals to, putting s equals to 0, 0 plus 0 plus 350, so it is 1 by 7, okay, 1 by 7. Now we'll come to sensitivity. What does sensitivity mean? So basically this sensitivity, right? Sensitivity means how much a particular variable is sensitive with respect to another variable, right? Let's say how much our output is sensitive with respect to the changes in the system. If the system changes slightly, if there is certain disturbance in the system, how much does the output also change due to that disturbance in the system itself. Okay, so that is what basically sensitivity mean. Okay, so that is what I have told you. Okay, if you want to write, you can write it now. Like, let me write the mathematical form, right? Let's say if we have one variable that a is a function of, let's say, another variable b, then the sensitivity with respect to, like, sensitivity of a with respect to b is given by, it is written like this. Let me write it down in different color, right? Sensitivity of a b equals to, simply, this is the partial derivative of a divided by a, partial derivative of b divided by b. This is a formula, right? What does this mean? Change in a with respect to change in b. This is just the ratio. You do understand that delta a by a and delta b by b, you understand this. Change in a divided by change in b. So that is what the mathematical meaning of sensitivity is. Change in a change in b. Okay, so this is the sensitivity. Now we'll do a few examples basically on the closed loop transformation, negative and positive feedback system, and we'll check how much sensitive is the output with respect to the with respect to the system, like the forward path and the feedback path, all those things, right? So what question was this? Let me check what question number last we did. Okay, this is the 8th question. Basically we previously did 7th, so 7th question, like 8th question is, we know the transfer function of a closed loop system for a negative feedback, right? For a negative feedback, it is g of s divided by 1 plus g of s into h of s. Okay, so I will not write the s here. Okay, just ignore the s for now. So it is g upon 1 plus gh. So our transfer function, right, is a function of both the forward path gain and the feedback path gain. So g comma h. Okay, g comma h. So like this is a transfer function. Now we will find the sensitivity of this transfer function with respect to forward path gain and with respect to feedback path. So let's first do the, okay, this is the question, right? So what I want to is I will write the question here. With respect to h, right? So these things you have to find. So our first will be t with respect to g, right? So it will be simply delta t upon t divided by delta g upon g. Now how we can write this as? We can write this as here g by t times delta t by delta g. Okay, delta t by delta g. Okay, so now we have to find the differentiation, partial differentiation of this transfer function with respect to g, right? So frequency we are assuming it constant, only we are varying the parameter g and doing the partial derivative. So I hope you understand what does partial derivative mean. So delta t by delta g delta t by delta g, what does this mean? So basically, right, this is simply, so we have to differentiate, right? So differentiate this one, right? Differentiate this one. So this is u by v form, so this will be square, and then we have to differentiate with respect to g in the first term, so this will be 1 and this term will be multiplied, so 1 plus gh whole square. Here we get g, okay, sorry, not g will be differentiated to 1, right, and this will be multiplied, the denominator will get multiplied, then this will be again differentiated for the second term, right, for the second term, okay. So second term is different, so here the differentiation of this will be h. I hope you know basic differentiation, okay, and simply g is multiplication, so what we are left with is 1 by 1 plus gh whole square. I hope you understand that we have the s term in the bracket, but don't worry, s is not varying here, so we will not write s for our simplicity, right. If you want to write in subjective papers, you will write s there, okay. So yeah, this is our delta t upon delta g. Now what we will do, find the sensitivity, okay. So s of t upon g equals to g by t. Now what is t? T is g by 1 plus gh times 1 by 1 plus gh whole square. So this is 1 by 1 plus gh, okay, this is 1 by 1 plus gh. So our sensitivity comes out to be 1 by 1 plus gh, okay. So this is basically our sensitivity. So like now let us find the sensitivity with respect to the feedback path gain, right. So let's do the second question. S of t with respect to h, so it will be simply delta t upon h, oh sorry, not h, t upon delta h upon h, so it is delta t upon delta h, right. So okay, sorry, this is not t, this is h upon t, okay. So now what I will do is simply find again the differentiation, right, partial differentiation of the transfer function with respect to h. Again the denominator will come out to be 1 plus gh whole square, but this time this will be 0, right, because differentiation of g with respect to h is 0 only, so that will be 0 minus, now this will be differentiation of this term, right, this term will be simply g, and the numerator was g previously, so it was g, so it becomes minus of g square by 1 plus gh whole square, okay. So now let me write the expression, right. This is like minus of g square, right. So this is h upon t, so h is this and t is what, g upon 1 plus g times one plus gh, so minus of gh upon 1 plus gh, okay. So what do I see? I see that this is only 1 plus gh and this is on minus, like minus you ignore, negative sensitive or positive sensitive, it doesn't matter, it is sensitive, right. So it is g times this gh times 1 by gh, right. So our transfer function is more sensitive from the feedback path, okay, from the feedback path gain than the forward path gain. So if there is some change in the system is generally in the forward path, right. System is, okay, I didn't draw the block diagram. Where is the block diagram? Yeah, this is system, right. So if there is some change in the system, this is a system generally, so it is not that sensitive to that change, okay. That's why we use the closed loop transfer function, that's why we use the closed loop system, right, to make it less sensitive to changes in the system, now. But the drawback is, if there is some change in the feedback, right, if there is some disturbance in the feedback, then the system will be more sensitive, right, to that change. The system will be more sensitive. By sensitive I mean, if there is change in the feedback, the output will also change much higher, but we don't want it to change. We want it to remain stable in what range that we want, in what desired output that you want, okay. So yeah, that is a drawback. That's why the closed loop systems, right, they are very expensive. So we have to make it like that they don't they don't get like disturbed by the outside noise, right? They don't get disturbed, right? They should not change. The feedback path gain, all those things should remain constant. The system, the normal system can change, this system can change, okay, but this feedback, right, this shouldn't change, okay. That's why we use a very costly system here, so that nothing changes over here. If there is some disturbance, it may affect this, but that's fine. Our output won't get affected by this disturbance, right? But due to this disturbance, the output may get affected. That's why we use costly systems here, okay. So it is very important point to note. So yeah, this is one thing about sensitivity. Okay, let me like do one thing for open loop system, right? For open loop system, what is the thing? Let me do this as 9th question. This is simply G, this is R of S, this is C of S. This is G of S, right? So like what will be our sensitivity, our transfer function with respect to G? We have only one parameter, the forward path, that is G. So what will be the sensitivity? So if I calculate, right, so what is the transfer function this time? It is C upon R, it is G, right? G. So what will be the S T by G? It is simply delta T upon T by delta G upon G. So it is G by T. So G by T. What is T? T is G only, right? And what is delta T by delta G? Delta T by delta G is 1 only. Differentiation of this is 1 only. So into 1. I'm doing this quickly. So we get 1. Okay. So this is the highest sensitivity, right? So generally this GH product, right? This GH product is like obviously more than 0. Okay. If it is more than 0, so this sensitivity is lesser than 1. So it is less sensitive. But in this case, right? In this case, it is the maximum sensitivity. If this gain changes somewhat, this will affect our output. This will affect our transformation. This will affect our output basically. Okay. If the transformation is affected, obviously our output will be affected. So sensitivity is maximum for open loop system. Okay, that's why we avoid it and we use closed loop system. Okay, we use closed loop system. Okay, so now what I will do is give you a few homeworks. Okay, all this you will go and solve. Okay, after that we'll restart our next lecture. Okay, so yeah, I think we have already like reached 1 hour mark, so we will restart with this questions, and after that we'll study all those concepts, right? Or what I can do is solve few questions, solve first 2 questions, then in next lecture I will give you 1-2 homeworks, and then we'll start with pole 0. Okay, let me solve this question, right? So like this question is given that we have been given an open loop system, and this time, right, we have been given the change. We have to find this delta T over T, right? We have been given change in the open forward gain, right? Let's say there is some external disturbance or there is some external noise. With respect to some external parameter, we get this change, right? Okay, now we have to find out what is the change for this out transformation, right, due to this disturbance. So we have been given this gain. So what is the sensitivity? Let me write this as the question. Okay, this is not one question, this is the 11th question. Okay, so what is the sensitivity of a open loop transformation? T respect to G, we just find it out. This is 1, right? So what is this equals to delta t upon t by delta g upon g. So we have been given delta g upon g, that is 15%. We can write it in terms of points also, like a normal numerical value also, or we can write it directly percentage. So our delta t upon t will be equals to delta g upon g, which is equals to 15% only, right? So yeah, this one was a pretty simple question only. So now here's the difference. There is, we have given the change in the forward path gain 15%. Now we have to find the change in closed loop, output, right? The transformation, if there is forward path gain of this one, right? So this will be interesting, because what you will see is this change, right, will be reduced. This change will be reduced. So I have just calculated. Okay, this is not the second question, this is the 12th question. So I have just calculated the sensitivity transformation with respect to the forward path. What is it? Let me check it. It is 1 by 1 plus GH basically. So here 1 by 1 plus GH for a transformation like this. So yeah, okay, I should not draw this diagram, else like it will be very confusing. Let me take this actually. Okay, I don't have enough space, just wait a second. Let me write h of s over here. Okay, so this is the closed loop transformation, right? So I have already calculated it here. What is the value? 1 by 1 plus GH. So I'll directly write it over here. 1 by 1 plus GH, which is equals to delta t by t upon delta g by g. Okay, so what is g times h? It is 50, it is 5, it is 250, right? So let me write this as solution. Another color. So it is 1 by 1 plus 250 by, what is this, 15%, right? 15%. Okay, so basically I can approximate it as 1 by 250 only. So delta t by t is 1 by 251 times 15%. So you see how much, by how much this is reduced, right? 251 times this is reduced. Okay, 251 times this is reduced. So here it was 15%. If there is some change in the system for 15% due to disturbance, then the output will also change by 15%. Transformation will also change by 15%. But here what we see, it is getting reduced by 251 times. Very interesting, right? Very interesting. So yeah, let me just, I have written down my values here. So it is always use the gate calculator, right? Always use the gate calculator for calculating 0.06 percentage, right? 0.06 percentage. This is actually plus minus. I forgot to write here. I forgot to write here. This is plus minus, right? This is plus minus. Okay, like it can change, go up, go down due to disturbance, right? Due to noise, it can go up, down. Okay, so this is plus minus, and this is much improved and much better. The sensitivity has improved much better. Okay, but if the instead of this dg upon g 15%, let's say if the feedback path dh upon h is 15%, plus minus 15, then what will happen? Let's say, so plus minus 15%, right? So what will happen? Simply this sensitivity t by h equals to delta t by t delta H by H, right? So we have already derived this. This is minus GH upon 1 plus GH. So what is GH? It is minus 250, and what is 1 plus GH? It is 251. So it is almost equals to minus 1. So what we see here is it is changing very highly, just like the open loop, right? Just like the open loop. So here delta T by T, right, it will be almost equals to plus minus 15% only. If you multiply minus with plus minus, it becomes plus minus only. So here we don't get the advantage of feedback. We don't get the advantage of feedback if our feedback path gain is like not that efficient and not that like efficient in like removing the disturbance, right? If it also changes, if our feedback gain also changes, then it will be harmful for our whole system, right? Our output will also change due to this. Okay, so we have to buy the feedback very costly. Okay, so here, okay, wait, where am I? Okay, I went, there is a glitch. So closed loop system is less sensitive with respect to forward path gain. That is the basically the main system, right? Main system. Previously what system was there? Okay, plant or whatever you want to say. But if there is no information of the parameters of G or H, then we'll consider with respect to G. So this is another thing. If they don't tell about sensitivity with respect to the feedback we have to find, or with respect to the forward path we have to find. So we'll by default we'll consider we have to find with respect to the forward path gain. Generally they don't ask with respect to the feedback for the sensitivity, right? So we are interested in the forward path gain only for finding the sensitivity. Okay, so feedback decreases the value of sensitivity. So this is the advantage of the feedback, as I already explained you, right? So for a highly reliable system, the value of sensitivity, right? The value of sensitivity should be small. Okay, like this is also one more thing, like basically you do understand, right? So if sensitivity is high, then our output will change and it won't be reliable, right? So if there is some disturbance in the system and the output also changes, so it is not reliable. Okay, if let's say this fan is like rotating, right, but if there is some outside wind is coming, but this fan will change its value, then there is an issue, right? This fan there is issue, so it shouldn't change its value. Okay, so yeah, this is one thing that we need to keep in mind. Now if our system is much less sensitive, then it is like only good for us. That's why we try to make it the system as much less sensitive to small disturbances as possible. Okay, so yeah, here like I've already same thing that I've written it down. Okay, you can read it. Okay, the one thing is the system the output should be highly sensitive for the input command for a good like this is like what I explained for a good control system. Basically the output should be less sensitive with respect to the forward path gain and the parameter variation, that is the feedback path in the system, but the output should be highly sensitive for the input command for good control system. Basically if I want to change the speed from the input, right, then the system should realize it and the output should change, right? But if I don't want to change, but there is some outside disturbance and it changes automatically, then I don't want that, right? I don't want that change. So yeah, that is what is written here. For a good control system, the output should be less sensitive to the gain parameter and other variables, but for the input it should be highly sensitive. Okay, that is what I have told you. So this is like homework for you. You will do this in the next class, and this is also another homework for you. Okay, take the screenshot of both of them. In the next class will come. Okay, so like let me quickly recap of what we did in this lecture. Okay, what did we study? Okay, here we are, right? So we first studied a negative feedback system. Okay, so there is some disturbance and C of S. Okay, so we found the why like what does a negative feedback system do? It tries to keep the output at the same level, and we found the transfer function from here. Okay, and then what does a positive feedback system do? If the output is slightly increasing, wait just a sec, sorry for the interruption. So for positive feedback system, right, what I was telling is if the output increases slightly, then the system will help it to increase further, right? And if it decreases slightly, then the system will help it to decrease further. So it is a regenerative thing. It helps it generates further more, gives it more energy, right? So yeah, then we derive the transfer function. Okay, these things you need to remember. Then I did told you few examples, oscillator and Smith here, and these are few points. Just just keep in your head, okay? And by default we'll consider unity negative feedback system if nothing is mentioned. If nothing is mentioned about the feedback, we'll consider it negative. If nothing is mentioned about the gain of the feedback, we'll consider it as unity feedback, okay? So yeah, now we done the concept of open loop transformation. It is valid for a closed loop system only. It is G times H, okay? G times H, okay? Then we related it with the unity gain negative feedback system. The closed loop transformation CLTF is equals to OLTF by 1 plus OLTF, okay? That is important. And we learned about the poles and stability of CLTF. We learned that stability of CLTF depends on the OLTF. This will further revisit in the next few chapters, okay? Just keep this in your mind. This further will get cleared in the next few chapters, okay? So yeah, now we did few questions on DC gain. From here we learned the concept of DC gain, okay? What does DC gain mean? And DC gain doesn't have a certain formula for the frequency domain. It changes according to the type of the system, right? But in the time domain, right, it is a steady state gain at t equals to infinity, okay? So yeah, from here we found about DC gain and cleared the confusion about OLTF, okay? Now we learned about sensitivity. What does sensitivity mean? What is the formula for sensitivity? We did questions on CLTF and OLTF, okay? We learned that it is more sensitive in the OLTF. It is like in open loop system, the sensitivity is maximum. CLTF reduces the sensitivity with the help of feedback, but if the feedback itself is changing, right, then again we will have the same problem of the output changing, right, output varying. So the feedback should be a very good system and very highly reliable system, so that it doesn't change with respect to outside disturbance, okay? That is important thing. But the system, right, main open this parameter, if this parameter changes, then our output doesn't change, okay? That is the main thing that helps the feedback, okay? So that is what we learned in this lecture. I did give you a quick recap, and these questions you will do, okay? So yeah, I did went a bit fast in the end because I have few work to do. So yeah, thank you for watching, and I will see you in the next lecture.